Hi everyone, and welcome to Graph Theory Visualized. I'm Jan, and today we're here to explore the wonderful and exciting world of graph theory. I created this series to showcase various concepts in graph theory that I learned in my undergrad, but the main goal is to teach you, the viewer, what graph theory is about, be it through these animations or the cool math games and interactive learning tool. Now, there are no hard requirements necessary to delve deep into what the topics are about, perhaps basic proofwriting, but just to follow along. Personally, I believe graph theory is mostly intuitive and almost natural to think about, and we will see why in the following. Now, on with the content. I'd first like to start off with a question. What does the road network of a city, one of the world's strongest, thinnest, and most conductive materials, graphene, and our relationships to other people have in common? All of these examples form networks. Graph theory is used to study these networks. Various real-world problems can be extracted and modeled with a graph theory solution. For example, could we perhaps know the minimum number of friends or strangers at a party of 6? This leads us to Ramsey theory and Ramsey numbers. It turns out the minimum number of friends or strangers is 3. We either know a minimum of 3 friends or 3 strangers. Or a more optimistic view, 3 more potential friends. Studying these real-world networks can be abstracted into a mathematical structure known as a graph. Formally, it is a tuple of 2 sets, the non-entity set of vertices, or nodes, and the set of edges, or lines. Looking at our examples, we can see vertices as the road intersections in the city, or the people in our social network. For the sheet of graphene, we can see each carbon atom as a node. The set of vertices is defined as a set of labels of vertices. We denote this with V of G. With 2 vertices, we can form edges. We can see an analog to edges in a graph with our real-world examples. For example, the roads in our city, or our relations with other people, can be seen as edges between vertices. Mathematically, the set of edges contains pairs of vertices, indicating a connection between vertices. We denote the set of edges with E of G. We often like to refer to the total number of vertices and edges in a graph. Notationally, the number of vertices is called the order of the graph, and the number of edges is called the size of the graph. For some more terminology, we call 2 vertices connected between an edge adjacent to each other. And we call edges that share a common vertice incident. Note that graphs are not always one big network, as there can be separate, smaller networks. It can even have no edges altogether. It can just be one node entirely. This is known as a trivial graph. Graphs are very powerful mathematical structures, not just because that they can help us understand the world a bit better, but also because they can lead to fascinating discoveries in its own field, as we will see in later chapters. I hope this chapter gives a bit of an overview on why studying graph theory can be exciting. Definitely look beyond the math jargon and think of some real-world examples yourself. In the next chapter, we will be learning about the concept of connectedness, some common classes of graphs. I hope you join me on this journey of exploring graph theory. Until next time.